Hello, in this video, I'm going to talk about the influence of vision on motor control. So we use and trust vision extensively and sometimes feel we can't complete a task without looking. So think like if someone is first learning to play piano or first learning to type on a keyboard, at first we feel like we have to look to be able to do it accurately. And as we learn that motor skill a little bit better and with more confidence, then we feel like we can execute the skill without looking. But there are all sorts of movements that we engage in and motor skills that we practice that we feel like we need to look at what we're doing to be able to do it accurately. We sometimes even trust our vision above our other senses like proprioception and equilibrium, even when that creates conflict. So like there can be like visual effects, this has been done scientifically, and this is done all kinds of times for entertainment purposes, where a visual effect can be created that makes it seem like the room is moving or something like that. And we will believe that visual input before we'll believe our proprioception and our equilibrium. This also happens in cases of motion sickness. Generally, what's happening in motion sickness is it's disagreement between our vision and our other senses like proprioception and equilibrium. And that's why like looking out the window in the car, or looking out over the horizon if you're on a boat, or, if we change what we're looking at, it changes our visual perception so that it will agree more closely with our proprioception and equilibrium, and that can help in cases of motion sickness. So it's like if you're in a cabin on a ship where the room around you appears to be stationary, it doesn't appear that it's moving, but your proprioception and equilibrium is saying that this room is moving. So in that case, your vision and your proprioception and equilibrium are disagreeing, and that could lead to motion sickness. Then you go up on the deck where you can see the movement of the water and you can see the movement of the ship relative to the water. And that often helps solve the problem because now all of your senses are agreeing. Vision is the result of sensory receptors in the eyes receiving and transmitting wavelengths of light to the visual cortex via the optic nerve, which we talked about in another video where we talked about the eyeball and vision. Monocular and binocular vision. So that is referring to whether we are using one eye or two eyes. So two eyes, binocular vision, is important for depth perception. So it helps us understand 3D characteristics of our environment. So 3D characteristics of objects that we might interact with, 3D characteristics of other people, or how far away something is. It's important to help us intercept moving objects. So like if we're hitting or moving a ball or catching a ball, we need binocular vision to improve our depth perception and make more accurate movements and more accurate motor control. If we are only using one eye, so monocular vision, accuracy and efficiency of the movement is greatly decreased. And that's especially the case as the distance of the object increases. So the further away the object is, the more we are affected by using only one eye. It interferes with movement planning and execution, underestimation of distance to objects and size of objects. So we think things are closer and we think things are smaller. So we underestimate the distance and the size. And we have difficulty correcting errors in limb movements when we're only using one eye, and it causes errors in movements, kinematics, and movement endpoint accuracy. So like if we're reaching to touch something, we might be less accurate in reaching the target. Okay, central versus peripheral vision. Central vision is also referred to as foveal vision, detects information in the middle 2 to 5 degrees of the visual field. So that is the point that we are clearly looking at and focusing on and can see very clearly. Peripheral vision is the other input in the rest of our visual field outside of that central 2 to 5 degrees. So we're getting about 200 degrees horizontally and about 160 degrees vertically in our peripheral vision. So both are really important in our movement planning and execution. So like take, for example, if we're reaching to pick up a cup off of the table, our central vision will fixate on the cup and we'll learn about size, shape, and distance with our central vision. The peripheral vision sees the arm. So as you're starting to reach for the cup, you're catching the vision of that arm that's reaching in your peripheral vision. So that's giving you live feedback about where your arm is in space to help you guide and correct for that movement to successfully reach the target of the cup. And then central vision is critical as you actually are grasping the cup so that you're seeing that you are reaching the target accurately and wrapping your hands around the cup. Similarly, locomotion, so walking or running, central vision guides us so we stay on the pathway. So where we're actually focusing our eyes is helping us stay on the pathway. And then peripheral vision is helping us update about the spatial features of the environment that we're walking in. So like we're looking where we're going, but in our peripheral vision, we're seeing things like branches hanging low, or maybe a bump or a pothole or something that we want to avoid where we're walking. So those things might draw our attention, and then we would move our central vision to those features to help us correct our movement patterns and avoid those obstacles. Perception action coupling. So that's referring to the coordination or coupling of our vision. In this case, the perception is the vision, and then the action or the movement. So we need to coordinate what we are seeing with how we're moving. So that's like hand-eye or hand-foot, not hand-foot, it would be foot-eye. Hand-eye or foot-eye coordination. Sorry about that. So our point of gaze is the specific location in the environment on which central vision is fixated at a given moment. So that would be like our central vision. So our point of gaze, what we're actually looking at in a given moment. Temporal coupling is meaning like timing. So point of gaze arrives at the target before the limb arrives. So let's say we're reaching to grasp a cup on a table. Our point of gaze is going to arrive. So we're going to look at the cup long before the limb makes it there to the cup. Spatial coupling, the point of gaze is going to arrive at the cup when the limb is not even halfway there. Okay, so we are already going to be looking at the cup. We're already going to be looking at the target before our limb is even halfway to reaching the cup. Vision provides spatial and temporal feedback. So it gives us feedback about where we are in space and the timing of the movement, so that we can initiate and guide the limb movements to be more accurate in our movement. Okay, so the time needed to make vision-based movement corrections. So like we talked about in the last video about proprioception, we can only make corrections to our movement patterns if the movement takes a sufficiently long enough time that we are able to integrate that sensory information and then send out an updated movement pattern or movement program out to the effector so that we can adjust and make corrections to our movement. So same goes for vision as it does for proprioception. And again, we'll talk about closed loop and open loop control systems. So the difference is whether we are using sensory feedback or not in correcting the movement. Okay, so the movement has to take a sufficiently long time to be able to use vision to make corrections. If we are anticipating the need to make a correction, then the minimum time of the movement may be shorter. Okay, so if you're expecting someone to throw a ball to you, then your time needed to make corrections and adjust your movement pattern to be able to catch the ball, that time needed is going to be less than if you weren't expecting the ball to be coming your way and need to be able to catch it. So like if the ball's a surprise, then you need more time to be able to prepare and execute that plan. But if you know it's coming, then it's sort of like you have that movement plan on deck. Like it's ready to go. You know that you're going to need to move in that way. And then you'll be able to make real-time corrections and be able to catch the ball more easily and more quickly. So like whether a person catches a ball depends on how fast the ball is traveling, from what distance, so how much lead time do you have before it arrives, and if the ball was anticipated. So were you expecting to have to catch the ball or not? And so those different factors are going to affect whether there's enough time to get your hands in place to be able to actually catch the ball in response to your visual feedback. Time to contact. So vision plays an important role in timing when to initiate an action and make contact with an object. So time to contact refers to the amount of time remaining until either the object hits you or you hit the object. So something's coming at you and it's going to hit you, or you are going at the object and you're going to hit it or catch it or whatever that contact might be. So we estimate that based on the rate of change of size of the object in your visual field, so in your retina. So you are actually, without having any idea, you are calculating essentially the distance and velocity of an object based on its size and how quickly the size of that object is changing on your retina. So you're able to estimate and time your movement based on how that object appears on your retina. So tau is a defined optical variable that specifies the time to contact. So it's specifying essentially the mathematical equation, which scientifically we can do that mathematical equation. We can perform the math and estimate these things, but you are doing this automatically without any knowledge of math or velocity or any of these things, but we're automatically estimating how long we have until we make contact based on the change of size of that object in your retina. So like a good example of that is when we're driving, and let's say you're driving behind another car and that car is suddenly stopping or slowing down. You are estimating how fast that changes and how much time you have until you rear end the person, until you crash into the car in front of you. You're estimating that automatically by judging the size of the car on your retina and how quickly that size is increasing. You're basically estimating the velocity that you're traveling at and how much time you have until you make contact. So based off of that, you then are modulating how hard you hit your own brake or whether you need to swerve to avoid contact. So you're making all of those adjustments to your motor plan and making all these changes in the way that you're driving based on the change of size of the car on your visual field. And that is tau. All right. Thank you so much for watching. Have a great day.